So the next to come is a flying fox. So it's hanging upside down on top and then drop before it glide to fly. Okay. So you can see their mechanism are still motor driven. So they are having a double crank mechanism to flap the wing up and down. And this flapping is accompanied also by passive wing rotation so that it can produce enough thrust. Now only for forward flight.所以这样的一个仿生蝙蝠，它其实是靠这个马达驱动它的这个拍翼机构，但是你可以看到它的这个手臂其实是很软的，它的这个翼面也是很软。的主要的目的就是在拍打的过程中，要行使翻掌的一个动作，因为只有在拍打和翻掌的同时，它才可以产生这个升力或推力。So this is another example of the bio-inspired robots. So this is a hopping robot. So it's imitating the kangaroo. So to do the hopping, so you can't just using a hydraulic drive alone because you need the impulsive force. So then you need some tendon and spring to help you doing the hopping. 所以像这个跳跃的一个机器人，要跳起来不是一般机器人都做得到的，因为你需要有足够大的爆发力。所以你可以看得到它的这个制动器是一个线性的一个制动器，一样的，很可能应该是用充气的方式才可以产生足够的爆发力。与此同时，在脚或者是脚踝那边，可能这个韧带本身要拉紧，这个储存势能，来提高这个跳跃的这个爆发力。So in order to jump, so you have a linear cylinder. Most likely is using the pneumatic or hydraulic drive. Even if you are using a motor drive, but it's still not enough to create the impulsive force. Okay, so what you see here now, electric motor is used for posture control, just like the tail posture. But in order to have the lead, now you need a air reservoir because it's the purge of the air that create the impulsive force. 所以你看到没有，马达在利用的地方一般都是一些不要爆发力的这个地方，但是你如果需要爆发力的话，你就需要用气动的这个马达来产生瞬间的这个爆发力。这个气动的马达这个做法很简单，就把气灌到一个气瓶里，的高压气瓶，然后突然释放，就好像气球吹胀过后突然释放，会产生很大的一个推进力。这个推进力再去驱动这个线性这个气动气动马达，就可以产生足够的爆发力，再配上这个弹簧，才能够跳跃。Okay, so you can clearly see that even this slow motion leaping that has to overcome the on-body weight, then you got to have the enough propulsive force provided by the pneumatic source. The pneumatic source have a reservoir to store the high pressure air, and then when released, or by purging, then you can have the leap or hopping. So last but not least, now we have the e-butterfly. Okay, this e-butterfly is weight much lesser, about 40 grams. So it has a large wingspan, even though you think it's a butterfly, but the wingspan could be as large as 1 meter for this man-made one. Okay. So they are flipping slowly, so you can count the frequency. Okay. So butterfly basically have two pair of wing, one is a fore wing and one is a hind wings. 所以这个蝴蝶基本上其实是不止两对翅膀，一个是前翼，一个是后翼，前一对后一对，所以它的这个低频底下拍动需要很大的这个翅膀面积才能克服它的重力。OK， 但这个蝴蝶在飞行的时候，它的这个动作这个相当颠簸，所以你要在蝴蝶上面安装这个摄像头做空拍的话，可能并不容易，或者可能要回推来减低这个震荡所造成的模糊。Okay, so these are some of the examples about the robots. Okay, let me see the slide that we have. Okay. So there are also other example. Okay, let me share you with other example as well.
Reach speeds of up to 300 kilometers an hour. Geese in flight ascend to altitudes of up to 8,800 meters. Visionaries, scientists, and pioneers of aviation such as Leonardo da Vinci saw flight as one of the greatest challenges facing humanity. For decades, they observed bird flight, analyzed its motion, and studied the anatomy of birds. They devoted great attention to the form and function of the wing and devised initial models. Otto Lilienthal was the first to build an aircraft that could glide through the air. But he did not succeed in deciphering the flight of birds. The best pilots are to be found in nature, and in engineering terms, the efficiency of birds' flight remains unparalleled even today. Birds are experts in efficient movement through the air. The muscular strength of their wings provides them with both lift and forward propulsion. During flight, their sensory organs help them to constantly measure and optimize their movement. They make the best use of airflow under all conditions. The company Festo, a global player in the world of pneumatic and electrical automation technology, likewise has superior mastery of airflow. The development and production of the latest generation of cylinders and valves relies on making optimum and efficient use of the flow of air in automation technology. As part of the Festo Bionic Learning Network, in which insights from nature are transferred to products in the field of automation technology, a number of filigree ultralight structures developed in accordance with bionic principles have already taken to the air. In air jelly and air ray, for example, helium provides the necessary buoyancy. These were lighter than air devices. Designing a bird that's heavier than air, however, proved a difficult challenge even for the experts at Festo. The company's engineers and scientists pooled their resources to achieve something that no aviation pioneer or scientist had attained before them: deciphering the flight of birds. The the idea for SmartBird was born.
Okay, so this video is long, so I will leave it to you to watch it after your class. So let's come back to our lecture, okay, so that we have more to cover. Okay, so why bio-inspired robots? So we already have these conventional robots for factory automations. Why do we bother about the soft robots? Okay, so below is a photo showing the robots for car assembly. So do you notice that one thing? In this kind of car assembly line, when robots are working, so there are no human operator at all. Why is that the case? That is because robots are actually pre-programmed to automate any repeated job. So they won't know any factory worker walking by. So they might accident that the robotic arm would knock some person and even cause the death. Okay, because these robotic arms are very powerful, forceful, but they don't have sense at all. So in comparison, human, animals has a lot of sense, and even their arm of motions are not as rigid as common robotics arm. So this compliancy provide the safety measure. So this actually is the reason why there is now a new motivation of developing a soft machines. So beside mimicking the anatomy of animals and human, so the whole purpose is actually mimicking the function, but using the new material, new sensor, new actuator. So let's come to the reason why we need to learn about the biological locomotion and manipulations. So we have many kind of locomotions. You have the terrestrial locomotion on land, on sea, and on in air. 所以这个动物的运动各种各样，可以在陆地上，可以在海里，可以在空气中。就比如猎豹的跑动，这个蜜蜂的这个飞行，还有海豚在水里游。So there are many examples of animal locomotion. You have the running of the leopard, the flying of the honeybee, also the swimming of the dolphin. But in terms of manipulation, you need more brain power. Okay, so to move object, you need a gentle and articulate hand. Okay, just like us, we can use our hand to pass a small thread across the hole of the needle. And elephant also quite smart. They can use their trunk to wrap around a small fruit. Their trunk also strong enough to carry the load like a tree log. 所以要用手去操作东西，这个是一个非常高的这个对脑力的一个能力要求非常高。你要能够把线穿过这个针孔，你的眼睛还有这个手的这个协调。大象的长鼻子也很灵巧，可以抓取食物，也可以负重很高。Okay, so let's look at the human locomotion and manipulation. We can run, we can swim, we can jump, we can hop, but we cannot fly, we cannot glide, we cannot soar. Okay, so basically, man can live and move around over land and sea. 所以人的活动空间要么是在陆地上，要么是海上，因为我们能跑能跳，能游，但是不能飞。OK，然后在这个操作方面，我们可以做一个很细微的这些操作，我们用这个机构，像手一样的机构去操作这个针线。OK，然后我们的舌头则是一个软机器，它不带任何骨头。So the example of the rigid body motion can be exemplified by the arm motions. On the other hand, our tongue is an example of the soft robots that can move without the presence of any skeleton inside. Okay, so how about the hard locomotion and manipulations? So conventional locomotion can be exemplified by the train that has the wheel rolling for the train to go through the linear motions. And you have the example of the turbine that produce thrust to power the flight of the aeroplane. And likewise, you have the engine to power the forward thrust of the ship and even submarine. So all these involve the movement of the whole body, and this is what we call locomotion. And about the movement of the object, we have robotics arm, and we have even this hydraulic gripper, and even a small uh, motorized gripper. Okay, so let's now define what is a machine and what is a robot. A robot is basically a machine, but that is capable of carry out routine and complex action, and they can be pre-programmed by engineer. 机器人，严格的定义应该说是一个可以编程控制它这个工作流程顺序及动作轨迹的一个机器。Okay, so the earlier robots are called automata, which perform pre-programmed tasks by CAM. The drive is powered by coil spring and steam engine. 最早的这个机器人我们叫 automata， 它相当于是一个自动化的机器，它可以行使预设的一些编程的任务。它这个当年没有这个电脑，他们的这个是通过这个 CAM 来完成各种各样的动作。Today, the modern robot can perform sophisticated tasks such as surgery, massage therapy, space exploration, manufacturing, and even code analysis. And the drive of the robots are electric, hydraulic, and pneumatic. Control of the robot are more versatile by computer program. OK， 今天的这个机器人能行使的任务更复杂，包括这个开手术啊、按摩啊，在空间上探索、制造，或者是甚至这个编码的分析。这个机器人的动作主要是这个动作来源主要是电动的、气动的，也有液压推动的。然后它们的控制可以通过电脑来实现。So what is the challenge of the rigid body robots? So the rigid body robots are widely used in manufacturing. They are built of rigid links and joints, but lack in compliance. Okay, being overpowered, they are unsafe for interaction with human. And to mitigate the safety concern in factory robots, space are usually separated from human one. 所以你可以看到，这个传统的这个硬体的这个机器人，都大量的应用在这个制造业，他们有坚硬的这个连杆跟关节，没有任何的弹性，他们一般都是力大如牛，但是跟人在一起工作的时候却非常危险，就如这个右手边第一张图，你机器人在转动的时候，如果一不小心撞到人的背，机器人看不到人，人看不到机器人 ，OK， 这个互相都不知道互相的作动，这个时候很容易造成意外的发生。机器人只要转一个这个90度，不小心撞到了人，人就可能这个脊椎就马上受损，甚至造成死亡。所以在在工厂里面，如果有大型机器，一般的做法是把这个大型机器人完全围起来，就没有所谓人机互动这回事，因为这个风险太高，机器人毕竟就不长眼睛的 ，OK， 你人看得到它还避得了，但你如果背着它，你可能就避不开了。So what is the advantage and disadvantage of rigid machines? Okay, one of the advantages is the very high load bearing capability. Okay, it can support very large mechanical work with very large inertia. So the work done is very consistent. The property don't change under the extreme force conditions. They can do a precise positioning and motion control. with the rigid transmission. Okay, however, there are some disadvantage. They are not universal. So they need, for every different task, there is a need of redesign and customization. So far, most of the customized part are the robotic gripper. Uh, in addition, this kind of rigid robots or machine are also difficult to operate in unstructured and highly congested environment. So they also have poor force control. 对机器人的这个缺点、优缺点，如下。这个优点就是它的高负载能力，可以做重复性精准的工作。但缺点就是说，它不是一个万能的这个机器手。OK，它需要每改一次动作，每改一次任务，你需要改变它的抓手，改变它的这个手臂，甚至于它不能在拥挤或无序的一个环境中工作。所以这解释为什么当日本可以做到这个很发达的机器手臂的时候，但是在面对要随时更换的这个制造程序的时候，还是输给了呃开发中国家这个廉价的这个人工，因为人工毕竟非常灵活，随时随地就可以变更适应变更的任务。Okay, how about the bio-inspired soft machines? So they also have their strength and weakness. So take for example, human fingers and muscular hydrostat are example of the soft robots. They are capable of doing delicate tasks in a cluttered and unstructured environment. So, so the aim is to actually achieve wide variety of tasks and adapt to the challenging condition within these tasks. In other words, they are going to be universal. OK，这个软机器手臂的发展，主要的一个目的就是做出一个有点像瑞士军刀这样的一个万用功能，在同样的机体的情况底下，它要负责不同的任务。OK，so let's see the two example. OK，so in the case for weightlifting, so this kind of the machine can do weightlifting of log, but you need a proper gripper. So elephant trunk can do both lifting of the log as well as picking up small particle. So in comparison, if you're going to pick up small particle or small sands, so you have to change your gripper or change your this carrier. So from the jaw to this kind of chauffeur. OK，所以你要这个抬起这个泥沙的时候，你就要用铲。OK，大象的话，虽然说比较笨，这个失去果实还是可以一颗一颗试，但是你如果是用这个硬体的这个夹爪，你要抬起木头的夹爪，要去抓一沙子，估计就不可能了。这就明显显示这个软夹爪或者是像橡皮这样的一个这个 manipulator 它的万用能力。So what is the vision of the soft robots? Soft robots has a continuously deformable structure with muscle-like actuations to produce motion emulating the biology. So they can bend, they can twist with high curvature. They can use their compliant motion to manipulate objects. They can even adapt to the environment. They are also capable of moving through a rough terrain and execute a rapid maneuver. 所以这个仿动物的机器或者是这个软机器，它的最大强处就在于它有这个柔软的结构，OK，可以弯曲，可以扭曲，可以利用这个柔软的界面，比较吻合的去抓取物体，可以适应环境，不同的这个地貌，都能做出敏捷的一个姿态的动作。So let's see the example of elephant trunk as a soft robot. So elephant trunk is basically, you can say a multi-segment pieces connected by muscle. Is capable of continuous articulation. It is strong, it is safe for interaction with human, provided the elephant are not agitated. So this also inspire other bio-inspired trunk and tentacle, completely made of the soft actuator. So the main property of this kind of elephant trunk is the bending stiffness and movement for bending. So let's watch two videos to show the strength of elephant trunk as well as the articulation.
What if you could use your nose to snorkel, or uproot a small tree, or smell water from several miles away? Well, elephants wouldn't be that impressed. They do it on the daily, thanks to what's inside their trunk. If you were to dissect an elephant trunk, it would actually look more like the inside of your tongue than your nose. Trunks, tongues, and even octopus arms are unique organs called muscular hydrostats. That means they're made almost entirely of muscle, and an elephant's trunk has a lot of them, about 40,000, compared to around 650 muscles in the entire human body. Normally, muscles depend on bones and joints to move and exert force. When we pick up a dumbbell, for example, our bicep pulls on our forearm bones, and that causes them to swing up around our elbow joint. But in an elephant trunk, there are no bones to pull and no joints to hinge on. Muscles take on that role instead. This makes trunks incredibly flexible, so they can move in all directions, and all those muscles mean they're powerful enough to lift hundreds of pounds, yet delicate enough to pick up a tortilla chip without even cracking it. But while trunks may be structured like a tongue and function like an arm, they are, in fact, a nose, and an exceptional one. An animal's sense of smell is linked to the number of olfactory receptor genes it has. And elephants, well, they have a lot of them, nearly 2,000, more than any other animal we know of. Bloodhounds, for example, only have about 800, while humans have even fewer. In fact, an elephant's nose is so good it can actually sniff out bombs. People have reported that African elephants avoid landmines in Angola. And in 2015, researchers put it to the test. Elephants were presented with a lineup of buckets filled with different smells, including TNT, the main ingredient in landmines. Out of 97 TNT samples, elephants detected all but one. Of course, their trunks didn't evolve as bomb detectors. They use their nose like we use our eyes, to find food and water, to avoid predators, and to map out other elephants nearby. That's like walking into a family reunion with your eyes closed and knowing exactly where everyone is. But if you can believe it, there are even more tricks up their trunks. When elephants traverse deep rivers, for example, they curve their trunk into a snorkel, and when bathing, they can use it as a hose, or more like a fire hose. One suck, a trunk can pull in as much as 10 liters of water, and the trunk's impressive abilities haven't gone unnoticed. In fact, if you stick a mirror in front of an elephant, one of their favorite activities is to open their mouth and check out their trunks. Let's admit it, if you had a nose like that, you would do the exact same thing.
好，看完这段影片，我们再看下一段。
Grazing up to 19 hours, eating up to 300 kilograms every day. None of which would be possible without their trunk. A fusion of their nose and upper lip. It's immensely powerful, capable of lifting up to 350 kilograms. But it's flexible too, allowing them to reach 7 meters high up into the trees. And it's also highly sensitive. On the tip of an African elephant's trunk are two finger-like extensions that can be pinched together to grasp even the tiniest morsel. Inside, it's even more intricate. The elephant's trunk contains more than 100,000 muscle units. within the muscle cells becomes firm and compressed, working like a hydraulic system, offering superb flexibility and rigidity. Different sections of the trunk can work independently and can bend or twist, lengthen and shorten. It's one of the most versatile tools in the animal kingdom. And when combined with their tusks, the elephant is formidable. Elephants' tusks occur in both males and female.
Okay. So 我们就看到这里。So next, what we're going to see. So you may have came across the documentary of the elephants. So let's see now what about the bio-inspired elephant trunk. Okay, so Festo also come out similar machines. Okay, but it's made out of pneumatic driven. So it has a segment of circular ring linked up by pneumatic actuator. So it can be used for this sucking and lifting of the weight. 所以我们就看看这个 Festo 模仿这个大象所做出来的这个机器这个象鼻。This kind of robotic arms is actually more difficult to control because of the many degree of freedom. So you can imagine for every segment, you have actually 3 extender powered by the pneumatic pressure. So at the front, you can install an arm with a wrist, okay? So all this has been possible by pneumatic driven. And then for the grasping now, they are using a mechanism called zamming. Okay, zamming is basically a sand bag which was vacuum. When vacuum is fixed in shape, when not vacuum, then the shape is deformable. And then this is a vacuum sucking, okay, at the tip. OK， 所以你现在看得到这种各式各样的这个仿生机器，一般现在都是气动的，就比如说这个像模仿象鼻的这个手臂，它全长大概是0.85米，然后半径是0.13或者0.1米，然后它的自由度有到12个自由度，整个重量有3公斤，2.9公斤，然后可以抬起的重量跟自身重量一样。OK， 它的工作压力要3个大气压。OK， 所以它的这个精度呢比较有限，大概是10个 mm。OK， 然后所以大概就是这样的一个能力。So from this example, you can clearly see this robotics arm is quite amazing because it's very light in weight. Its weight only about 3 kilograms, but the capability of lifting is also about 3 kilograms. Okay, so the accuracy of this robot is not so good for positionings. It's only as much as 0.01 meter, so or 10 mm. Okay, plus minus. Okay. So this you can see now the trade-off between strength and the precision. Okay, what are the other soft robots? Okay, so there are many soft robots developed. There could be very stiff one, and there could be very soft one. 所以我们说的这个软机器，其实是一个大范围的一个机器。这些软机器其实还是有这个骨头的，或者是有框架的。那框架可以是非常硬的，就比如说这个跑步机器然后它也可以非常软的，就是好像这个像这个乌贼的这个机器，也可以是像充气的这个机器 ，OK， 都非常软。比较硬的，它负重能力都比较大。然后机器的种类也很多，在地上跑的、水里游的，或者是在空中浮的 ，OK， 或者是帮忙做这个rehabilitation 的。So there are many use of the robots. It could be for land locomotion, underwater locomotions, air locomotions, and even it has been used for the rehabilitation curve. So 我们之前说的这个软跟硬，它其实指的是材料性质的这个硬度。所以我们就来看看不同材料性质的这个杨氏魔术，它有多软。最软的就是你们吃豆腐 ，OK， 这个豆腐非常软 ，OK。硬的呢，就如金刚钻这么硬，金刚钻还可以用来切割这个金属，或者甚至于你的这个吸金源都是用金刚钻一划，在这个晶体的表面刮出一个刮痕，你就可以沿着这个刮痕把这个吸金源给掰成两半。Okay, so what you can see is the two extreme of the material with different hardness. The hydrogel is very soft, like tofu, like your this alginate hydrogel. The very hard one are diamond. In between them, so there are soft material like silicon. There are soft silicon. There are hard silicon. Your cartilage is harder. Your artery are hard. Your liver is even harder, and then followed by the skin. 所以你最常见的这个身体里面的组织，你可能并不熟知。OK， 最软的这个硒胶，其实要比我们的这个肌腱，要比你们的这个韧带还来得软。然后你的血管，大血管要比你的这个肌腱跟韧带还来得硬。然后比较想不到的，原来你的肝脏也是一个硬家伙 ，OK。当然，皮肤要比肝脏的组织更硬 ，OK。然后我们常见的这个轮胎的这个橡胶 ，OK， 要比你的这个皮肤还来得硬。所以更硬的塑料也是有的，就像你常用的这个 PET， 然后你肌肉，也比较硬。实际上你的韧带，这应该是肌腱，肌腱比肌肉更硬。肌腱的这个硬度差不多跟尼龙相比，然后木头更硬，骨头最硬，然后再来就是我们常看到的这个 fiberglass。So you can see the comparison of engineering material with the biological material. They are different in hardness. So if you now look at the hard part, our tooth is hardest, followed by the bone, and then that explains also why animals like lion can have their tooth tearing down and crushing the bone. Okay, then followed by the bone, then you have the tendon, which has a reduced stiffness and modulus, followed by muscles, skin, liver tissue, artery, and cartilage. Okay, so in terms of engineering material, the hardest is diamond, followed by steel, followed by fiberglass, and wood, nylon, rubber, silicon rubber. Yeah, so that's the range of the rubber material. Okay, next we will see the classification and between hard and soft robots. So for soft robots, you have a continuous body, then you have hyper redundant. What does it mean? Soft material, if you make it long, so that is a continuous body. And when long body is wrapping some object, then there will be redundancy, means that some part that you cannot control, they will deform by itself to fill up the gap. In comparison, the hard material is made use of the redundant piece. That redundant piece, uh, it, that discrete piece can be non-redundant, just like our robotic arm. Two arms is enough to define the space, okay, in 3D. Okay, but if you introduce more than three arms, more than two arms, okay, more than two linkage, then you have extra redundant degree of freedom to control. So this show you the example of hard and soft body. Okay, if you now want to move the hand beneath a block, okay, so this arm and wrist got to do the curl like that. And then for the elephant trunk, you can do many way. Okay, the hand position can be any way depending on the curvature of many degree of freedom. But for our rigid robots with reduced number of linkage, so you are lesser to control. Okay, but because of the flexibility, even though it's difficult to control, but it is possible to grab something more gently and more uniformly as compared to the rigid robots. 所以这个分类主要是在自由度上面的分类。你这个钢体结构，你的这个自由度一开始设计起来就相对有限，而你这个软机器它是一个连续体结构，它的自由度非常高，所以控制起来比较难。但是虽然控制起来难，但是它如果要让它掌握一个物体，它可以比较柔顺或者是比较轻巧的握取。So this is a classification presented in the earliest literature. So they show you the number of actuator, material strength, what are the material. So for rigid, there are fewer actuators, discrete. They are made out of metal or plastic. Okay, so the capability is very high accuracy, very high load capacity, but they're dangerous. The dexterity, how flexible, how robust they can to hold something is very low. So they only can work in very structured environment. So the object they can hold up is also fixed in size. The conformity to the obstacles is none. They cannot avoid obstacle. So they're very easy to control, very easy to be planned the path, very easy to sense. Okay, the inspiration is coming from the limbs. But if you're talking about the soft robots, the other extreme, so you have infinite degree of freedom. So you have a continuous actuator, a large strain, rubber rod material, the capability, their accuracy is low, load capacity is the lowest, but they are safe. They have high dexterity, they can work in structured and unstructured environment. They can handle variable size object. They can conform to the obstacle. Okay, but their design is difficult. So that's why the current practice is you are handling something in between the very soft and very hard robots. So you have the discrete redundant object, which is adding more degree of freedom to the rigid body. And you have the hard continuum. So you have introduced some hard part to the soft robots so that you can have reduced number of the actuator, but still able to do the continuous motion. So this is the table that bridge the two. So now, a very important thing about the requirement for the robots is the interaction with the environment. So you can see that, so the hard robot usually rely on the soft link, okay, or the actuator at the joint to allow the motion. Okay, so this kind of hard robot can be presented in the form of the arm, also presented in the form of leg. Okay, so to have the proper interaction with the environment, yeah, soft robots, as you can see from the video, yeah, it can do a lot more. Okay, but the gravity play a part to the robot's positioning control. Let's see the example. 我们就来看一下这个软机器跟硬机器的差别。这个软机器跟硬机器的差别，我们就拿一根悬臂梁做比较。OK， 你如果是一个软的这个材料做成的一个悬臂梁，在重量底下，这个软材料的自重都会造成它形变。OK， 所以你要再加上制动器的话，你要知道你的姿态，知道你的角度，去克服自身重量，你才能够实现准确的定位。所以为什么说这个软制动器比较难控制？因为它软到就是说重量会造成它的大形变。所以你的所谓的软硬的一个分野就在于它会不会在自重底下形变。So one of the very simple criteria to determine is it hard material, is it soft material is whether it will deform under its own gravity. Soft structure will deform under its own gravity, but hard material will not. So that is the main criteria to differentiate the two. Okay. So the challenge of soft robot is how to control that, and also you want certain strength within it. Okay. So you got to integrate actuator and sensor, and even added the computation to deliver the required behavior. So here I quoted one picture from the science robotics. So they present the grand challenge of soft robots. So this is the topic to be covered. There are enabling technology that require sensor, actuator, material fabrication, compliance, energy, and computation communication. There are also the system synthesis, so that require the understanding about the mobility, swimming, crawling, digging, walking, running, jumping, climbing, and flying. So in this course, we are spending our first lecture on this animal locomotion so that you're understanding the system level motions control. And also to be included is manipulations and human-robot interaction. And then the part we cover a little bit is about the theory. We have modeled the actuator sensor, but we did not cover the modeling of the whole system, except the simple mobility analysis. Yeah. So application is what we would like, okay, but it's leave up to the student to explore. Okay. So beside that, then we look at the level, some important challenge. So to build a human-like body, you need material. So you need the material that can deliver functions. You need energy source. You need the sensor actuator. You like to see, you like to hear. All these are the functions. To build all this up, you need the fabrication. So that fabrication could be hierarchical. So one of the grand challenges is indeed the functional material that deliver all this. Okay. So now let's see. Okay, we're going to have a short break. Okay, let's see. We'll start from 9. Okay, we can carry on for a little bit more. Okay, let's have a review about the rigid robots. OK， 我们现在来看看这个，回顾一下这个钢体机器的历史。虽然我们是想设计软体机器，但是我们还是得了解一下钢体机器的这个发展史。So the early history of the robotics can date back to Greek time. That is before that is 350 BC. Okay, Greek mathematicians succeeded in building a mechanical bird that used steam to power itself. We call it robots or you call it toys. So it bear the same concept, okay, but differ in the complexity. So this is the simplest form of the robots. It can deliver the motion you wanted. Okay, in 1920s, the Czech writer coined the word robots in his play. Okay, and later in 1940s, Asimov gave us a three law of robots that can be used to define what is a robot and what is not. Okay, so and yep, so in the what's the rule? What's the three law of robots? The first law is a robot may not injure a human being. Yeah. So that's not true. True in actions. Okay. Allow human being to come to harm. Okay. So that's not really true. Robots can harm. Okay. In 1950s. Okay. So robotics arm has been used in the factory in the assembly line. So in the car production line, so you can see the robots doing all kind of chores, replacing the human. And then next is the history of the human-like robots or humanoid. So humanoid was first used in, yeah, this robot's name was first coined in 1920s. So there were theory about the human, uh, about the stability. Humanoid actually come only appear in 1970s. Okay, Honda had many versions of the humanoid, P2, P3, and then later Asimo. Okay, so all electric motor driven. Okay, and then on United States, they also come many different versions. Bipedal humanoid, Atlas. Atlas come a lot of progress until today. Okay, so the robots in Japan, okay, you have many different kind of machinery. So in Waseda University, you have the Warbot like humanoid, and in Tokyo Institute of Technology, you have the ACMV, okay, mainly robotic arm that's good for manufacturing in industry. Yep. So, let's see what else. So let's have a quick look about the early history of robots. You might think this is a toy, okay? But this toy actually lay down the foundations of robots development. Okay, we have the robotic birds, we have the robotic lion. Later, you have the automated movement, and then pre-programmed and sophisticated tasks. So let's have a look of this video. Okay, for the robotic toys. So in 15,000, okay, indeed, Leonardo da Vinci created a mechanical lion with the ability to walk. So this is one form of the animals robots. So let's have a watch. So their foot are wheels, but because of the legged motions, so this is still considered bio-inspired uh, robots. So this is a present to the King Louis for the birthday by presented by Da Vinci. Okay, next we'll take a look at the robots during the Edo period in Japan. So there are these robots that can do the serving of the tea. So they are lifting a tray with a cup of tea, and then after going a straight line, you can turn to the audience and serve the tea. Yeah. And after you finish it, you can return. Okay, but because of this kind of automata have no view, so it is actually the human to decide the directions. It also need the interruption by human to make sure it go through the straight path. Okay. But the perfection of the automata happened in the Switzerland, which is well known for their watchmaking. So in 1974, the Swiss lockmaker Pierre Jacques Droz and his son completed 3 automata: a writer, a musician, and a draftman that can draw a clock. Okay, let's watch the movie and video.
One of the most remarkable realizations of CAD technology is a device in the shape of a small ball. It's perhaps the world's most astonishing surviving automata.
So in that old day, you may not have a computer program, but you have a CAM to store the motion needed
It's on this card.
to write a letter.
It's writing by a 240-year-old machine. Favorite machine is one of the most magnificent automata of the 18th century. It's this boy, this writer. He was built in Switzerland by Pierre Jacques, Switzerland's greatest clockmakers. The aim was, I think, to mechanize reason and automate passions. Jacques Droz was about 50 years old in the early 1770s. He designed and built this masterpiece. Inside the ball are almost 6,000 parts. What's astonishing is that every one of these crafted components has been refined and miniaturized to fit completely inside the body of the boy himself. What Jacques Droz did was to use the technologies of homeostasis, of miniaturization, to build really a true automaton. Inside the little writer is all his source of energy and all the machinery that drives him. He works on his own.
所以这是用机械的方式做运动的控制，一边移动这个纸张，一边控制这个毛笔。其实说白一点，差不多就是用 XY stage 的方式去完成这个写字的这个功能。So the writing is actually based on the technology of XY stage.
Followers read their shaped edges, translate these into the movement boys are.
So each cam stores certain motions. So if you need more motions,
Cams control
then you need a stack of cam.
exactly how much pressure is applied to the paper so as to achieve beautiful, elegant, and fluid writing. This sublime machine, Jacques Droz had reverse engineered the very act of writing. But the mechanical boy contained one perhaps even more astonishing feature. The wheel that drove the cams was made up of letters that could be removed and then replaced and reordered.
所以从某个角度来讲，就是活字印刷。
possible to make any
OK，
sentence, but it allowed the writer to be programmed. This beautiful boy is thus a distant ancestor of the modern programmable computer.
Okay. So of course, this writer, this automata is look a lot more complex. So in comparison, the work done about the steam power man are less impressive. Okay, but there are some of the bipedal robots that can walk. Okay, walking is also one of the ability that cannot be achieved by previous automata. OK，在这个瑞士钟表师做出了写字的这个小男孩之后，这个后续的发展就有发展一些叫用脚走路的机器人。OK，这个机器人要讲精细程度，并不如写字的小男孩，但是他的这个能用双脚走路的能力，却是挺特别的，特别是在那时。一般还是用轮子来滑动的年代。OK， 要用双脚走路的几个机器人，我们就可以举例这个本田的这个 Asimo 跟这个 Boston Dynamics 的 Atlas。OK， 它们的差别有多少呢？我们来看一下。So let's have a watch and compare the performance of two humanoid. One of them is developed by Honda, is named Asimo. The other is developed by Boston Dynamics, is named Atlas. Okay, so what's the difference? Asimo is 1.3 meter high. It weighed about 54 kg. The walking speed is very low, 2.7 kilometer per hour. If you divide it by 360 seconds, okay, or 60 minutes, you find that the walking distance is limited. Running speed is 6 kilometer per hour. Okay, let's see the running speed. I do a quick calculations to turn it into meter, because we know that the man's maximum running speed limit is 10 meter per second. So this 6 kilometer divided by 3600 is turning out only at 1.6 meter per second. So it's rather slow running. Okay, the walking cycle is adjustable in terms of strike. The grasping force is 5 kg force a hand. And look at here. So what's special here? I want to highlight. So they are driven by the servo motor. They are driven by the harmonic speed reducer. So this is all hard metal. So they are very heavy. So that's also explain their slow running speed. This slow running speed was just now calculated to be 1.6 meter per second. Okay, so they have the foot area sensor, gyro, and acceleration sensor, rechargeable battery. Working hour is 1 hour. Okay, so very limited. Okay, on the other hand, this Boston Dynamic one, it didn't show you the actuator. Okay, but as we can see just now, it was actually a pneumatic driven for certain forceful drive. Okay, so let's also see. Yeah, the robot is a programmable function manipulator designed to move material tools. So this is the definition for industrial robots. Let's have a watch of this video. For a quick one. 所以绳手再加上这个输送带也就变成了这个机器手臂。Okay. So this is the crane. Yep. So it can be used for laying the brick, and then next you have the recycling exercise for the robotics arm. They are doing the separations, what is wood and what is the ceramics. Okay. This is a collaborative robots. They have to work together to do the job. Usually robot do a job alone, so it's easy to be pre-programmed. But now if you want to coordinate 2 robots, now 4 robots, then it's more difficult. And then this is a 3D printing of the house. It's also make use of a crane together with the concrete dispenser. So this concrete dispenser is almost like squeezing out the toothpaste, but here this is a paste of concrete to build the house. So eventually it built such a house. But imagine you got to have a robotic arm larger than the house so that you can print it. So these are cooker machines to cut the hole into the cylinder of carbon fiber. So this is a sorting or packing robotics arm, packing up the brick into a pallet. They can take 3 at a time or 2 at a time. You can see the robotic arm usually have a consistent speed. The reason is partly due to the electric motor not able to giving the impulsive force. Okay, so now we come to the some definition of the industrial robots. So you look at the robotics arm, you basically have a hand, you have the wrist, you have the forearm, you have the upper arm. So between the forearm and upper arm, then you have the elbow. That elbow is an actuator. Also between the hand and the forearm, there is a wrist. This is also an actuator. So this kind of elbow or wrist is usually for rotational motions. And for the forearm, it's needed then you can have the linear motion. For the hand, it is a gripping motions. So at the shoulder, then you have the even larger motor, okay, to control the motions. Okay, so usually the actuator are electric motor, but recently there are also development of the pneumatic motor for this purpose. So the pneumatic motor are lighter in weight because the external pressure source can be placed outside the arm. So the gas transmission to the pressure gas transmission to the arm could be carried out by some horses. So here you see the 5 components of a pneumatic driven robotics arm. You basically have a compressor to max air, a reservoir to store the air, and then one or more valve to control the air, and then a circuit control the valve, and then the actuator to use the air to do some job. Okay, so the air compressor will convert and store the energy into the power source into compressed air, and then the reservoir store the air. Okay, so pneumatics in robots are now replacing electric motor and servo. Okay, for material handling, welding, machinery. Okay, but this good thing about the pneumatic drive is involve the fluid motions, lower safety risk, less maintenance. The cons is, yeah, the speed control is not that good. So you need serving the high pressure source and prone to moisture. Okay, now let's have a look at the other configuration of the industrial robots. Okay, here this is mainly the motorized driven robotics arm. You have the controller to operate the parts of the arm. You have the arm consisting of shoulder, elbow, and wrist. Okay, so it's almost imitating our human arm. And then finally the end effector. Okay, each of the joint has a degree of freedom, and because now you have shoulder, elbow, and wrist, then now you have 3 degrees of freedom. And next, you have the up and down motions, control left, right, and even forward, backward. And effector is the hand of robotics arm. So you have the gripper, vacuum pump, magnet, and welding torch. Okay, and then drive behind them is the engine or motor that move the link to the designated positions. The drive can be hydraulic, electric, and pneumatic. And then sensor will receive the feedback from the environment. So it has limited sense for sight and sound. Okay, the whole purpose of the sensor is to make sure that the 2 neighboring robots do not collide into each other. And then also assist the end effector, the gripper, to adjust the parts variance. This is good for pick and place robot. Okay, pick and place robot use a lot of visions to identify object. So let's have a look at different kind of end effector. So you can have simple mechanical grip, suction cup, magnetized suction hook and scoop, and you can even install the spot welder gun and even the saw to the robotics arm. Then you see these robots can cut the wood a lot into a stool. 所以你可以看到这个手爪各式各样，从最简单的机械手爪，这个真空吸盘、磁吸盘、钩子，或者一个勺子，你可以安装一个锯子，让这个机器手臂来切出一个木凳子。Okay. So what type of sensor you have a tactile sensor to sense the touch and force. You have the proximity sensor and range sensor to avoid the contact. You have the ambient sensor for temperature, pressure, fluid flow, and more commonly you have the machine vision these days. So the purpose of sensing is to make sure you have a safety distance away from neighboring robots and neighboring men, and then also good for positioning and part inspections. Okay, what are the drive? The drive, as we can say just now, you have the hydraulic actuator, which is very powerful, just like what it has been used for the crane. Okay, 所以液压的这个制动器这个是非常强而有力，就像它用在伸手一样。气动的就比较力道比较小，它一般还是用这个转动或者是来回的方式去做动。然后这个电动的话，基本上有4伏马达、部件马达，还有这个直接的驱动的马达。一般都是转动，你要把它转换成线性运动的话，你需要一些滚珠螺杆之类的这个器件。在这个液压的制动里面，我们主要是看到它的这个很大的力道。So you can see that hydraulic drive is very good for lifting very large weight. Take for example, in the lifting of a whole car, you can use the principle of hydraulic by using the small area with large displacement. You can lift up a heavy object on the bigger cylinder. Okay, so hydraulic drive also good in terms of speed, but needs for extra flow space to house the hydraulic compressors. But it has a problem of oil leak. Okay, it can produce a linear motion. So this is a good example. There is a crane that use a hydraulic drive. So in the next example, you have a pneumatic drive. You can see this kind of blue pipe. This is a pressurized piping source. It's good for small robots with a pick and place with a fast cycle and using open and closed gripper. It drifts under the load and also they produce translation and rotation. Simple and low cost, but you need the external pressure source. Okay. 然后我们看到我们最常见的这个电动马达也常用于驱动你的这个机器手臂。Okay, 然后你这个机器手臂用的电动马达，基本上是直流电或交流电的4伏马达或部件马达。它的组成基本上是一个定子跟转子，然后再控制电源。这个定子上面都缠绕着线圈，你线圈流激活，这样的话可以吸引这个定磁铁的这个转子一步一步跟转动，这转动速度通常都非常高，都是几千到几万转这个每分钟。但是你如果要把它转换成手臂的速度，你就要减速。所以减速所需要的用到的就是这样的一个内圈跟外圈的这个两个这个齿轮，这个齿轮叫做 harmonic drive speed reducers。它基本上这个是外齿轮是有静电的，然后内齿轮这个红色的部分是软的。OK， 所以就根据这样的一个转动，它可以把这个转速给减缓。OK。So next about gripping. For the gripping, then you have the imitation of our finger. So fingers are also rigid gripper, but now with the soft interface. What about soft interface? You have the soft tissue surrounding the bone, okay, and then you have the skin. So in imitations, we can actually place a soft rubber cover around the rigid tips, okay. So or in the further, you can actually put the tips to be completely soft. Okay. So this will then have a better grip on the object. Okay, this is what we call under actuation. Okay. So in the case of rigid body, rigid tips, you cannot hold shape of particular shape. Previously, if you can handle the circular shape, you might not be able to handle the tube. Okay. So that's the reason why you need the soft interface. Okay, but introduction of soft interface will introduce the hysteresis. You may not know the exact force you apply upon the return and relaxation. This is unlike the rigid one. Okay, that you know pretty sure. So let's have a watch about the video before we going to have a break.所以你看到没有，它的指尖已经放了这个塑胶垫，并不见得全都是硬体的结构。OK， 然后这个机构本身还有就是叫 under actuation，OK，你不完全控制它的那个位置，但是你控制它的那个抓取的时候，可以完全掌握这个被抓取的物。So in the case of under actuation gripper, you don't precisely know the actual position, but the finger can conform to the shape of the object to be grabbed. So this is one of the difference between the common robots, robotic arm that you need to know the precise motion. Okay. So with the three finger, you can do many kind of grasping. You can grab the cylindrical one, spherical one, and even a block one. And you can even scissor like pinching. Yep. So these are fingertip grabs. So this is encompassing grabs. And then next you even have spheroid grabs for the long object. And now you can do the pinch of the bracket. And holding the scraper part. Okay. And now you can use a scissor grab, okay, between your pointer finger and the middle finger. So the grasping can range from low force to high force. Okay. And this is what we call the adaptive gripper that can grab many things. OK， 我们现在就上到这里先休息一个10分钟，然后我们接着再上这个软机器人的这个部分。OK， 软机器人部分也有好多变化我们等一下会接着谈。So let's have a break for 10 minutes. We'll come back at 11:10. Okay, see you shortly for break. After the break. Yep. OK，各位同学好，上到这里有什么要疑问的吗？So any question from the class? So you have a question, raise it so that we can address you. So if there is no question, let's continue the class. 如果没有问题的话，我们继续下一个部分。OK，就来看看这个软体系的新发展。So let's see what's the new development of the soft robots. So one important development is the hydrostatic skeleton. So what is hydrostatic skeleton? So it's basically just a cylinder filled up with liquid. And this cylinder is made of muscle. A muscle surrounding a fluid. That muscle is reinforced by connective tissue fiber. So that is very different from what you see as an exoskeleton. So in the exoskeleton, you have robots inside the implant. In the exoskeleton, you have a shell outside a nail. And in the hydrostatic skeleton, then you have the water pressure inside the wall keep the body bulging. So many animals won't like the body moved by peristalsis using the opposing circular and horizontal muscle that act on the hydrostatic skeleton to change the body shape. Okay. 那我们现在讲的是液压跟骨骼。什么叫液压的部分呢？它基本上是在一个腔体里面的液体，它的压力撑起了你腔体这个外墙的这个结构。这样的液压骨骼由于骨头，我们人骨基本上在这个人手肌肉之内，然后那个。像其他昆虫或其他几种动物，它有外骨骼，它是外骨骼保护着内在的肌肉。这个 hydrostatic skeleton 这个静态的这个液压，这个骨骼呢，是这个液体的压力，把柔软的这个腔体给撑起来。腔体基本上有结缔组织加固。同时，这个结缔组织可以不同，还有这个肌肉有不同的方向，有向上的肌肉，有环状的肌肉，让这个像蚯蚓一样的这个液态骨可以做收缩伸长的动作。So what are the example of hydrostatic skeleton and muscular hydrostatic? So you have many others. So what we learn about the hydrostatic skeleton are mostly the caterpillar and also the earthworm. But our tongue are actually muscular hydrostatic. Okay. So molars are the one that is known for their soft body, soft muscular skeleton. Okay, so they have the muscular foot, head, and then the visceral mass containing most of the organ and flesh matter that segregated the calculus cells. Okay, so let's watch the video. Let's see the species under the molars. You have the well-known squid, you have the octopuses. The other class are bivalve, they are scallop, they are clam, they are mussels, another class is called gastropoda. Okay, like snail, like slug. Okay. So there are many videos to see, but let's see the interesting mollusks. For example, 下一个分享一下这个影片。So let's watch the video. So this might be, yeah, a general introduction. We may not see the full video.
Just around 150,000 different mollusks that emerge today. But when they first appeared over 500,000 years ago, mollusks were tiny creatures changing around under a protection shell. How did the struggle for survival create so many variations on the original body plan? This is a world of taxers hungry on their protein-rich, sweet-tasting flesh. Mollusks have survived because their body parts manage to change as new challenges arise. The basic toolkit of a mollusk is evident in the outline. Most mollusks have some kind of foot. For many, including the abalone, with the foot muscle bestows mobility. When the foot brings them to food, mollusks eat by using a unique grasping toe called a patula. Covering the vital organs is a false skin called the mantle. It's the mantle that secretes the trademark body armor of so many mollusks, a shell. Leafy hornmouth is developed just 3 well-placed ridges along the shell. These ridges add just enough thickness to foil a crab's attempt to get a shell-breaking grip. Since no shell provides perfect safety, some mollusks have added another method of defense. They develop means to outrun their enemies.
So we just finish this basic and then we move on. Okay, actually the octopus is also a kind of mollusk, except that it has no shell. 所以这个八爪鱼跟贝壳类是同样的亲戚。八爪鱼的贝壳跑到哪里去了？跑到它体内去了。它已经强到不需要这个贝壳来保护，因为它变成了猎食者。为什么它变成猎食者呢？它有强而有力的这个爪，它是抓其他动物，包括螃蟹的一个猎食者。So actually, it's an evolution of mollusk from clam to octopus. Clam was a weak animal that we were worried to be hunted. They got protection for the hard shell outside the body. The hard shell protect their soft flesh. Okay. But the hard shell alone is not the best protection. Okay. But this protection appears to be the defense, to be the aggression, the attack. So this evolution led to the development of the octopus and squid, which are very good hunting other uh, animals like that used to eat the mollusks. Okay, so the shell of these squid is still there, but inside their body, and no more out of the shell. So squid is known for their octopus is known for their very agile arm or tentacle. They can do the catch. So let's see how this octopus do, okay, in with their arm.
Octopuses have elaborate cardiovascular and nervous systems. Their cardiovascular system includes three parts: two pump blood to the gills, and a third moves blood throughout the rest of the body. Unlike human blood, octopus blood is copper-based, which makes it appear blue. The octopus nervous system includes a brain, but 2/3 of the octopus's neurons are found throughout its body, especially in its arms. This means the arms have significant local control and sensory capabilities. They may even still reach or grasp after they are severed, and their suckers are able to sense chemicals. In other words, smell or taste. Octopuses are intelligent. Some scientists believe octopus intellect can be found in their ability to use tools and exhibit foresight, retain complex memories, which helps them navigate mazes and solve puzzles, and to use visual cues, which helps them differentiate between human individuals. Octopuses have also been shown to play, an activity considered a sign of intelligence. Most octopus species will only live between 1 and 2 years. Much of the short lifespan has to do with the octopus's reproductive process. When octopuses mate, males may be strangled and eaten by females. Males are often smaller than females, so they become overpowered and sometimes cannibalized once fertilization is complete. While females survive the mating process, they die after laying their eggs. Female octopuses guard their eggs for up to 8 weeks. During this time, the female's body self-destructs through cellular suicide until she dies. Octopus ink is deadly, even for the octopus. The ink is a seemingly innocent mixture of mucus and melanin. Melanin, the same dark pigment found in skin, hair, and eyes, also happens to contain the chemical compound tyrosinase, which can impair a predator's sight, taste, and smell. Octopuses and other cephalopods may use their ink to distract, confuse, and paralyze their predators. This mucus mixture may even block a fish's gills, causing the fish to suffocate. If an octopus cannot escape its own ink, its respiratory systems may be compromised, causing the octopus to suffocate and die. Octopuses are masters of mimicry and camouflage. They can trigger cells just underneath the surface of their skin to change color. The cells, called chromatophores, contain sacs of pigment that can turn various shades within milliseconds. Some octopuses, such as the common octopus, can also imitate textures. They can warp small segments of their skin, called papillae, to match textured environments. Species like the mimic octopus are able to not only camouflage themselves, but also manipulate the shape of their bodies to impersonate other animals. Their wily mimicry, along with many other curious characteristics, are just a few reasons why octopuses are captivating creatures of the deep.
Okay, after watching the video, we see that yeah, these octopus are very capable in doing many things. Okay, so let's look at their arm structure. Okay, their arm structure is basically consists of some muscle. So you have, this is called longitudinal muscle along the whole leg. You have the transverse muscle, and you even have the oblique muscle. Okay, So this enables the arm of the octopus to do a capable job of catching. Okay, and then it's all surrounded by a tissue sieve. Okay, so imitating this kind of octopus arm are the first soft robots developed by a Japanese researcher Hirose in 1977. Okay, at that time he was not using any soft part. He was just simply using um, multiple linkages made of the hard part. But he's using fiber to cable pull to control that. Okay, that's the same idea of using the cable pull to drive the arm, to drive the finger for grasping an object. So the degree of freedom they has is multiple. It can grab things due to the multiple degree of freedom. So subsequent soft robots are elephant trunk inspired. So you can see this. So the first one was using this shared memory alloy wire, okay, to do the control of multiple segment, okay. So this elephant trunk actually bear the same principle as your catheter. 如果同学有做过这个内窥镜的，你就知道这个跟大象鼻子一样，它是一个连续体，它是靠弯曲来控制方向的。OK，只是内窥镜的话，它还受到管壁的影响。So what is the basic construction of the elephant trunk? It basically has a backbone structure, segmented and continuous structure to provide the bending stiffness. And then next you have the two pair of muscle or two pair of cable. So that you can bend left and right. And alternatively, so you can have the backbone and control set be replaced by the fluid filled bellow and fluid filled tube. So this is what has been done by Festor in their manipulator. So the common method of building it for bending motion, you can have bi-layer. Okay, so if one of the layer is getting tighter, so it bend. Okay, or else you can have the transverse cable. Yeah, if you have a transverse cable contracting, then they are doing the thinning. Okay, so this is the use of the some cable pull or tension pull shape memory alloy. So next is the inflation type. The inflation type is actually like blowing a balloon, but this balloon is fiber worn. So there is a fiber reinforcing the wall of the balloon. So if you blow it up, you simply bulge up and getting shorter. But if you now connect this balloon to a hard substrate, so this ballooning up of the top layer will cause the bending toward the bottom substrate. Okay, and then next, there is a passive compliance of the structure. So this is a fish fin gripper. So they can also do some bending. Okay, let's see some robotics tentacle. Okay, 我们来看一下这个robotics tentacle. So let's watch the video of the robotic tentacle. So it basically has the three balloon, okay, segmented balloon, so that you can do the bending in a circle, okay. If you have only two tube, then you will have only the two-dimensional bending. But because now you have the three tube, then you can have the three-dimensional bending. Okay, so this is showing you how the inflation can cause the bending motions. Okay, why inflation cause the bending motions is depending on the length chain. It's just that you are pulling a fiber, okay, so that due to the differential chain in the length, you can have a bending. But what about a single tube? If you now have the pneumatic air artificial muscle with a fiber angle of 54 degree, upon inflections, of this fiber tube, then you will have the bulging sideway, but shortening. So why does it shorten? Because fiber has a fixed length. So if it's bulging up to keep the fixed length, then it must be shortened in length. So the original shape is this long. Upon inflections, it becomes shorter, but thicker. Okay. Upon deflections, it get longer, but thinner. Okay. So this is how a fiber worn pneumatic air balloon or muscle, you call it, can do the control extension and contraction, yeah, by pressurizations. Okay, so this is actually the depressurization. Okay, so next we'll see the example of such a good use of new pneumatic muscle. Okay, so here's a typo, extension upon depressurization. Okay, we'll see this air muscle driven robotics arm developed by Festo again. Since Festo is a well-known uh, this air, air-driven muscle. Okay.
In the case of the humanoid, the task was to transfer the biomechanics of the human musculoskeletal system to a technical construction. The element for the realization of this aim is Festo's fluidic muscle.
Okay, can you see the video?
Permanent feature in production systems, the fluidic muscle is proving to be a universal tool in a surprising number of applications. It's simply a completely new type of pneumatic drive. Its properties are similar to those of a real muscle, but it's operated with air. When the fluidic muscle is filled with air, its diameter increases and the length contracts. This enables flowing and elastic motions. The initial force of this artificial muscle is extremely high, and its dynamics resemble those of the human muscle. The humanoid can either follow pre-programmed motions or be controlled in real time via a data suit and data gloves. This means it can be used in places which are either inaccessible or too dangerous for humans. Eric's arm also utilizes the fluidic muscle. It attempts to simulate as closely as possible its human role model. Through the aid of Eric's arm, even more complex movements will be made possible. 30 artificial muscles move the bone structure and joints, a construction not encountered in this form in the world of technology. In combination with Festo's latest piezo-proportional valves, this technology enables precise control of the construction's forces. Coordination of the muscles and valves is made possible by cutting-edge mechatronic systems and software. Eric's arm is also of great interest to the future of robotics, as it can interact almost naturally with humans.
好，我们看完这个，我们再继续。So next, what are the other robotics arms developed after the elephant trunk? So here is another example using pneumatic driven arm. They have the 3 segment, they have 3 tube. Okay, so in that way you can control curvature at the 3 segment. Okay, so let's have a watch.
The Arc-Arm, a soft robotic manipulator, is a biologically inspired continuum robot that mimics the remarkable maneuvering abilities of elephant trunks and octopus arms. Arc-Arm consists of a 3-section continuum manipulator that is made of pressurized rubber tubes with rigid blades joining the continuum sections of the robot. Each section of the robot consists of 3 pressurized actuators that can expand or contract to produce bending in the trunk. Given the desired position of the robot, a computer calculates the required pressure in each actuator based on a mathematical model. Here we can see the last section of the trunk bending through all 360 degrees. Biologically inspired maneuvering. Now we can see Arc-Arm demonstrating its various biologically inspired maneuvering skills. Arc-Arm is holding a basketball just like an elephant would hold it with its trunk. It is moving into various positions while maintaining the grip on the ball with 2 of its sections. Arm is equipped with a motor at the base that rotates the whole arm through 360 degrees. Arm is using all the three sections to maintain the grip on the ball while
Okay, so from the video you can see one of the problem of the control of this out arm. Okay, so actually it's good for grasping, but to turn 360 degree you still need a separate motor. So you can see the limitation of some of these soft robotics. It has to be complemented by conventional motor. Okay. 所以这个传统的这个仿大象的机器人，它其实它只是绕了一个圈，它比较合适的就是抓取的时候抓取球状物。OK， 所以它现在这个简单的结构只是3束肌肉，3束这个充气的管，并不足以做到很复杂的这个形状。OK， 所以你看到没有？它其实只是绕成一个弧线去抓起一粒球。然后它真正转动的时候是靠另外一个转动的马达。Okay, so next we can see the robotic fish. So this is a robotic fish developed by I think either MIT or Harvard. So they are using the pneumatic source to create these bending motions, do undulation for fish to move. So let's see how the undulation go. 我们来看看这个电影。
We are developing soft-bodied robots, and there are three important things to know about these robots. First, their bodies are made out of soft silicone, and they can bend and twist because of that. They are also inherently safe to be around. Second, because of their body's capability to bend and twist, these robots are capable of very compliant motion, and they are also capable of very rapid, agile maneuvers, which pushes the envelope on what machines can do today. And thirdly, the robots are self-contained and autonomous. In other words, we can package the power source, the computation, and the actuation and sensing needed for these robots to deliver their motions.
Traditionally, soft robots have been either self-contained or capable of high performance, but not both. So in one part a little bit larger.
Okay, so we'll come back to here. So you can see that even though it's a robotic fish with pneumatic power, so you still the gear pump. Okay, the very important part of that is there is a pump to do inflation of the fish tail. Okay, so now next we come to the discussion about difference of pneumatic and hydraulic and electric actuator. So what's the difference? So for electric motor, you are converting electric energy into torque. So stepper motor will rotate instead. This is very useful